Hello, hi everyone, welcome back to the channel. So today in this video lecture we'll be solving this problem, allocate minimum number of pages, which is a very popular problem for coding interviews, and it is also solved using binary search. So let's read the problem statement. You have n books, each with ai number of pages. So ai basically represents the ith element of an array A, and we have n as the length of that array. We have m students which need to be allocated contiguous books, with each student getting at least one book. So each of the m students must get at least one book. Out of all the permutations, the goal is to find the permutation where the student with the most pages allocated to him gets the minimum number of pages. Out of all permutations, that means we have to divide those books to those m students in a continuous manner such that the number of pages which each student gets must be minimized. The maximum of the number of pages which m students get, must be minimized. That's what we want to do in this problem statement. Now, return -1 if a valid assignment is not possible. So in case we can't assign books to all of the m students, in that case return -1, and allotment should be in a contiguous order. Okay, so that means we can't allocate book number 1 and let's say book number 3 to the first student. We have to allocate book number 1, 2 and then book number 3 if I want to allocate 3 books to the very first student. So that's the case. We have to take the order in consideration. So let's better understand the problem statement using an example. Okay, so let's take this example. We have 4 books represented by this array A, where each element represents the number of pages that each book holds, and this m represents the number of students that we have. Okay, so now let's allocate the books. One of the ways to allocate the books would be allocate 12, 34 to the first student, then allocate 67 and 90 to the second student, because we have two students. So student number 1, student number 2. In this case, the student number gets 34 plus 12, that is 46 number of pages. The pages would be 46, while in this case the pages would be 67 plus 90, that is 157. Okay, now the max of 46 and 157 would be 157. So this is one of the ways to allocate the books to the two students. Let's take another way. Another way would be to allocate 3 books to the first student. That would be 12, 34, 67, and 1 book to the last student, that is 90. And the first one would give me 12 plus 34, that is 46. 46 plus 67 would be 113. So the sum of these pages would be 113. So that is going to give me 113. Okay, let's take another division. Let's allocate book number 1 to the first student, and the rest of the books to the second student. That would be 34, 67 and 90. So max of and that is going to give me 193. So this is another way to divide these books. Now, is there any other way to divide them? No. Now out of these 3 ways, we can see that this one, that is this allocation, where we allocate the first 3 books to the first student and the last fourth book to the second student, is the most optimal, because the maximum of the pages which are allocated to each student is minimum. Hence the answer would be 113. That is the answer. And we can see that we are allocating the books in the continuous order, in the order they're given in the array. We'll see how this fact will make our life easy in solving this problem. So what is the intuition to solve this problem? Now we can observe that we have to minimize something. We have to minimize the number of pages which are allocated to the students, that is minimize the maximum number of pages allocated to the students for a particular combination, for a particular allocation. Now again, the pattern is same. Find minimum number of pages such that the books are allocated in contiguous order, and the maximum number of pages allocated must be minimized. Again, binary search problem. Fine. So think about binary search when you have this kind of problem. Now let's see how we can solve this problem. What is the intuition? So we get the intuition. It's again a binary search problem. Uh, we we must be capable of identifying this pattern at this point if you have followed the videos till now. Now let's say we take this array which has 4 elements, and m represents the number of students that we have. So what is the strategy to solve this problem? We can see that let's call the minimum number of pages to be x. Now this is something we want to minimize. So x represents the minimum number of pages which are possible for a particular permutation, for a particular allocation of books. That so basically x represents the maximum pages allocated to a particular student. Okay, and out of all the possible permutations, this x is the possible minimum number of pages which can be allocated. Like we had 3 combinations here, we had 3 permutations here, and out of these permutations we can see that the maximum pages allocated in this case, which is 113, is minimum out of all. Now now this is what we are calling x. Okay, now that's what this x represents here. Now if I can allocate x number of pages to a particular student, then I can always allocate x plus 1 number of pages to the students, because here you can see that I could allocate 113 pages and this is the minimum, but I can see that I can always allocate 114 pages. Why? Because notice other cases. In this case the maximum is 157. We can allocate 114 pages to a particular student. Here for the second student, if we take this combination, we must have allocated 114 pages before we arrived at 157. Fine, obviously. Similarly, I can also allocate 115 pages and so on till the upper limit. Okay, that's what I'm saying. I can allocate x plus 1 pages. I can also allocate x plus 2 pages until the upper limit. What is the upper limit? Now think of the extreme case. Think of the case when we have only one student and we would allocate all of the pages to that student or all of the books to that student. In that case, the pages the student would get would be the sum of elements of the array. Okay, so sum of array elements, while I goes from 0 to n minus 1. Fine. And now if x is basically the minimum, I can't go lesser than x. That means allocating x minus 1 pages in any case to any student is not possible, such that this is the maximum of all the pages allocated to the student for that particular combination. Say in the same fashion, x minus 2 is also not possible, and so on till what is the left extreme? It would be 0. The left extreme would be 0, because let's say we have all the elements as 0 in the array. In that case, I won't be able to allocate any page to any student at all. So now we have our search space. This is my search space, and these are the bad pages. Let's call them bad. These are the good pages. Let's call them good. Okay. Now perform the binary search over this search space, and the target element is this x. Okay. Now what is the definition of predicate function? How would I check if a particular guessed value, let's call it mid, while performing the binary search lies on the bad side or on good side? How can I check that? So we have guessed that, okay, I'm saying mid is the number of pages which I would be able to allocate to a student, and that mid represents the maximum pages that has been allocated to the students for a particular combination, and this mid is minimum of all the possible permutations. How would I make sure that? That's the main challenge of this problem. Let's see how we can do that. Okay, so let's say mid is basically the guessed answer. Now I want to check if mid lies on the bad side or on the good side. Okay, and we know that we have m students. So for that, what I would do is I will simply start traversing this array, and I will keep a variable sum. Okay, now I will start traversing this array from the very first position, and I will keep summing these elements without crossing this limit mid. So let's start that. 12. So let's say for this particular test case, the guessed mid is 113. The answer 113 is the element we have guessed. Now let's start traversing this array. So we sum 12, then we move to the next element, that is 34. We add it as well. Then we move to the next element, that is 67. We add it as well, and we can see that we haven't crossed the limit of 113 yet. Here you can see that 12 plus 34 plus 67 is equals to 113. Now can I add 90? No, I can't. That means to the very first student I would allocate these 3 books, and the pages that we would be able to allocate to the student number 1 would be 130, and the students and the number of students to which we have allocated the pages would increase by 1. That means I will stop allocating books to the student number 1 at this point, because after this point, if I would allocate the number of pages, that is going to cross my limit of mid. This is the guessed answer. So the students variable, I would keep a students count. Let's say stdcnt, student count. It was 1 initially. Now it has become 2. That means to one student I have already allocated, and the rest of the books has to be allocated to the student number 2. Now let's see that. Now 90 would be allocated to student number 2. Does 90 cross mid? No, it doesn't. And now we end this array. We stop traversing the array. At the end, all I have to check is the number of students to which I have allocated the books, such that the number of pages allocated to each student is not crossing this limit. Now we haven't crossed the limit, and let's see the number of students. The number of students are 2, and that's what we require. M is also 2. We want to allocate the books to m students such that the maximum number of pages allocated does not exceed this 113, and so we return a true for this case. 113 lies on the good side. So this can be my potential answer. So answer variable would be initialized to 113 and the search space will be reduced. Since this mid lies on this side, let's say it lies here, and I want to find the smallest mid for which my conditions are satisfied, and that minimum will always lie towards left. So the search space will be reduced to low to mid minus 1. Now I will search for the possible answer towards left side where we have already got one of the answers here, one of the integers on the good side, but we want to find the first integer which satisfies the conditions. Okay, so that's the case. Otherwise if this mid, let's say if this mid lies on the bad side, that in that case, that this is case number 1, and in that case we just reduce the search space to mid plus 1 to high. Why? Because the element which satisfies our conditions will lie on the right side over this. Let's say mid lies here, this is mid, and since this is not satisfying the conditions, the mid which satisfies the conditions lies on this side. So that's why I am reinitializing the range to these values, mid plus 1 to high. Now these are the two cases that we have, and that's how we perform the binary search. Okay, so I hope you got the idea where we are going, and now let's see the implementation of these ideas on the next slide. Now before you watch my implementation, I would recommend you to pause the video here and try to implement the solution by yourself. It is very easy. If you have followed till now, it would not be that hard to implement. All we have to do is to just implement the usual binary search. We have the lower limit, we have the higher limit, and just try to implement this boolean function which I have explained here. Okay, now let's see my implementation. Okay, so this is my implementation of minimum pages function, which takes in this array representing the number of pages which are present for each book, the number of books, and the number of students to which we want to allocate these books. Initialize a variable sum to 0. Here I am checking if the number of books available are less than the number of students. In that case, we would have students left without books allocated to them. In that case, I would return -1. This condition is given in the note of this problem statement here, and that's what I'm handling here. Then I will add the pages of all the books that we have in this sum variable, and let's initialize our boundaries. Left to 0, right to this sum, and answer to a very large value. Now let's run the usual binary search, find the middle element, and here I'm checking if this mid lies on the good side or on the bad side. So this is the boolean function which returns if this mid lies on the good side or it lies on the bad side. So if it lies on the good side, then I will store this mid as an answer here. This mid basically is an answer, and reinitialize the boundary to low to mid -1. Otherwise, reinitialize the boundaries to mid plus 1 to high. Fine, so that's all, and at the end return this answer which will store the minimum number of pages allocated to a particular students for a particular combination. Now let's see the definition of this boolean function is valid. Okay, so this is a definition of the boolean function. It takes in the array, the number of elements in the array, the number of students to which I want to allocate the books, and the middle element or the mid that we have guessed in the binary search. That means the pages allocated must not cross this element, this number. Initialize the students variable to 1. That means we have at least one student to which I want to allocate the books. A current sum variable which simply represents the running sum or the number of pages allocated to the current student. iterate over the array from the first element to the last element if at a particular point the number of pages in a particular book exceeds this current min. So this is basically current min, not current sum, it is current min. So this is basically the upper boundary. We can't allocate books, we can't allocate pages more than the current min. And if we have any element in the array which is greater than this current min, that means it is not possible to allocate books such that the maximum pages allocated are equal to this current min. Hence we return false right from here. Otherwise we check if adding the current number of pages to the sum we already have for the current student, if it exceeds the current min or not. That means if it is possible to allocate these number of pages to the current student such that it does not cross this min. Here it is crossing. So if it is crossing, then that means we can't allocate these extra pages to the current student. We have to allocate these pages to the next student. So we increment the number of students by 1 and the current sum will be reinitialized to array of I, because till the current sum that we previously had, we have already allocated the pages and we can't allocate more. And here we can see, and we just have to allocate the pages in the order they are given in the array. Okay, so that's why I am reinitializing this current sum to the current value on which we are standing. Okay, so the same idea, let's say we had 1 2 3 4 these type of elements, and this current min is basically stores, let's call it 7. It stores 7, or let's say, okay, it stores 7. Now this is the running sum. The running sum would be 1 2 3, that is 1 plus 2 plus 3 would be 6. So till this point I have allocated 6 pages to the first student, but if I want to allocate these 4 more pages, that would give me 10 pages to the first student, but it is not possible to do so because the upper limit is 7. The maximum pages we can allocate are 7, and hence I will allocate these pages 4 to the second student. So I will make a partition at this point. So the current sum will be reinitialized to 4. So this will be erased and it will be reinitialized to 4, and we'll start traversing the rest of the array from this point onwards. That's what we are doing here, and the students will be incremented to 2. Fine. Now at this is basically a simple check. If the students that we have counted exceeds the limit, if we have allocated the pages to the students more than the students we can, then we return false. That means it is not possible to be within the limit of this current minimum while allocating the pages to exactly m students. Hence we return false right from here. Otherwise, if the sum basically does not exceed the current minimum limit, then add these pages to the current student. Give these pages to the current student. Fine. And if I never encounter these two conditions while running this for loop, that means I have successfully allocated the pages to the students such that the maximum pages allocated does not exceed this current min, and hence I return true at the end of this function. So that's all. That's how this is possible function or is valid function. I'm calling is valid here, but it is possible. Okay, that's okay. You can just do it as is valid. This is valid, and I hope you got the working of this is valid function. And let's discuss the time and space complexity. Since we are just performing binary search over a search space, the time complexity for performing binary search would be log of m, where this m is basically the length of the range, that is from the L to R or from low to high, while this n represents the number of elements in the array, because for log n times, here for log n times I'm calling this is valid function, and this is valid function take big of n time complexity because we are iterating over each element of the array here in this loop. That's why n multiplied by log m, while the space complexity is constant because we are not using any extra space. Fine. So that's all. Let's jump to the code implementation part. Okay, so this is a solution class. Let's define the minimum pages function, minimum pages allocation function, which takes in this array. Let's call it books array, and the number of students that we have. Okay, now let's calculate the size of this books array, initialize a low point and check, and here we have to check, we have to handle the base condition. If the number of books that we have exceeds the number of students which we have to allocate those books, then that means we would have some students which would be left without books, and in that case I will return -1. Otherwise, initialize two pointers, low and high, and simply iterate over the books, and sum all the pages in the books. So high basically stores the upper limit, while low stores the lower limit. Okay, so this low to high range is basically the pages that we have. Now just run the usual binary search. Low is less than or equals to high. Find the middle element. Low plus high minus low divided by 2. Check if this particular middle is valid. So pass in the books, this mid, the number of pages which I want to allocate. If it is valid, then that means the answer, this can be my potential answer. Which one? This mid. So I have to initialize another variable. Let's call it answer. Let's say 0 or -1. Then here the range, since this mid lies on the good side, the range will be updated to high as mid -1. The range here is being updated to low to mid -1. Otherwise, the range will be updated to mid +1. The range is allocated here to is reinitialized to mid +1 to high. Fine. And at the end I will return answer. Okay, so let's define this is valid function. So this is basically a boolean function, is valid. Let's take in the vector or the array that I have, books array. The middle element, let's call it current min, or and the number of students that I have to which I want to allocate. Let's initialize a running sum. Let's call it running sum to 0. Let's iterate over the books. Okay, now if the current element exceeds the current min, in that case I will return false right from here. Otherwise, I will simply check if the running sum exceeds the upper limit, that is current min. If it does, then I'll simply count the number of students by 1. So students, so we have to initialize another variable. Let's call it students, initialize to 1, which represents the count of students to which we have allocated the books. So since the current number of pages cannot be allocated to the current student, I have to switch to the next student. So that means the students will be incremented by 1, while the running sum will be reinitialized to this current element. Okay, and I will also have to check if the students exceeds the limit. If the students exceeds the limit at in any case, then I will return false right from there. Otherwise, I will simply allocate the pages to the current students, and at the end I will return the I will return false because I have never encountered. I will return true because I never encountered these two situations while running this for loop. Fine, so in this fashion this is working. And this is the implementation in C++. Let's see the implementation in other languages. This is the implementation in Java, and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and continue with me in this binary search playlist. We'll be solving a few more problems, and I hope to see you all in my next video.